Good afternoon or good morning or in between. Let me start. I will proceed my own experience and then explain in this journey of 35 minutes, including question answer. And probably at the end of 25 minutes or so, I will stop, or 30, depending on that. Then we will take some questions from the audience. Let me start the presentation. I have chosen this topic because all of us say, at least the perception, that neural network is a black box. All of us say that. But is it really a black box or a white box, or not completely a black box but not a white box? So let me try to unravel some of the things. And in machine learning, artificial intelligence, deep learning, neural network is being very, very widely applied. So some very brief introduction. I'm not going too deep into the theory of neural network, but a brief introduction and the discussion points. The first one is a brief introduction to neural network. Then the black box conundrums, puzzles, why you say black box. Then some attempt to unfold the black box mystery. Then two case examples, discussion of the results and conclusion. This is the agenda which we will package within 35 minutes. And let me just start that. The first one, the word artificial is important. Artificial neural networks. It is a strong contender in the analytic world for classification and prediction problems. You have CART, you have logistic regression, you have other supervised techniques such as random forest and discriminant analysis and all that, which are statistically oriented. And neural network is non-parametric and non-linear complex relationship model building exercise. Predictive accuracy is well known. It's considered a universal approximation. Anything can be found by neural network, approximate with a terrific accuracy. So some applications, credit default, buyer versus non-buyer in marketing example, classification of risk using neural network. So all classification problems and predictive analytics, neural network can be used. Handwriting recognition, handwriting letters, this also we can use neural network. Plenty among many applications. This is a basic thing everybody knows. This is called a perceptron. That the perceptron is the weights which you have here. You have input variables. You have the function which quashes this whole thing into a weighted average. A function could be a sigmoid function. It could be a Gaussian function. It could be a linear, non-linear function of any kind, or hyperbolic tangent. And input, process, and output. And the bias behaves like an intercept in a regression model. So this is the network topology which all of us are familiar. And when we have to talk about predictive accuracy, we use what is called the multi-layer perceptron neural network topology with hidden layers. For example, here you have two input neurons and you have the hidden one, 1, 2, 3, 4, 1, 2, 3, 4, two hidden layers with 4 nodes, and then the output comes. So initial start, you give some weights and bias some numbers, and the activation function could be something like a sigmoid function, which is a logistic function, it's called. And you try to change the weights by feed-forward method. The weights are changed every time is recursive way, and finally you get the output, the neural network. This is the architecture, a perceptron, and you have multi-layer perceptron. The hidden layer, in fact, is closely associated with the point that black box. Sometimes you say, what is happening inside? You do not know what is happening. How the neural network is learning the training set and the data set, how it is learning is not clear. That is the criticism, one of the criticisms. Other than that, there are black box methods. So every time the weight is changed, and then finally you have a rule that you minimize some sum of squares of errors till that best thing is found out, you are able to continue the iteration. This is how it goes. Now, the black box conundrums, I just want to say some of the statements you would have seen. It can approximate any function, but it gives no insight into the relationship between the predictor variables and the outcome. Because I cannot write even the final equation in neural network. Something is happening. The weights of a particular stage is a function of the weights of the previous stage, which is a function of the previous stage. It goes on, and it will be perhaps with the greatest difficulty, you will have to write sum of several functions as an equation, which will not help us. So in other words, that what is the precise relationship between y and x in a supervised learning, it's not possible to capture in the neural network. That is one. But it's universal approximation, if you are interested in accuracy. It lacks explanatory power. Suppose something changes, what happens to y? It cannot say. In a logistic regression, you have a precise form, you have parameters estimated, and you are able to find out something. So this is a problem. Explanatory power and the hidden layers, what is happening inside, we are not able to say. The other problem which is popular, which is very important for us to unravel is, if you are running neural network for the same data set I am running, even with random seed and all that, the two neural networks with different weights are possible. Identical result, but weights are different when you are given neural network topology. In other words, you get an answer, more or less I may tally with you, but my weights are entirely different, the synoptic weights. So it is very difficult in a practical world to interpret the weights. Whereas if you take a traditional technique, I can interpret the slope, I can interpret the arcs, I can do something. That is the problem. In other words, black box conundrums. I say these are the riddles. Some are true, some are not true. We will try to address. So some attempt, how do we propose to do that? The hypothesis I have is, neural network is not completely a black box. There is definitely adequate weightness that can be derived out of the black box. That's the hypothesis I have. It's not a complete black box. I'm not saying it's a weight box, but it's not a complete black box. It's an unfair criticism. And apart from predictive accuracy, the second hypothesis I have is, the relative importance of the attributes can be quantified in a neural network model as much as a model like the logistic regression. It's possible with little more extra efforts. And we are going to use two case examples to find out how to unfold the black box mystery. Is it possible? If so, why? Then sensitivity analysis of the changes in the input variables have been done to capture the changes in the classification matrix and odds. This is what is done. And then a comparative picture between neural network and logistic regression is derived for certain important concepts like the quantification of relative importance, odds, and all that in the business context, and try to say, is neural network really a black box? So the first example I pick up is from the classic book, Naresh Malhotra's Marketing Research, a small data set, because neural network requires large data points, but still I have taken that. And in this data set, you have three input variables: the attitude towards brand, attitude towards, I think this red one is not pointing it out here. Anyway, attitude towards the product category, attitude towards the shopping category on a scale of 1 to 7. 1 is unfavorable, 7 is favorable. And the outcome variable is whether somebody is a brand loyalist. So you are predicting the brand loyal as a function of attitude towards brand, attitude towards product, attitude towards shopping on a scale of 1 to 7. This is the problem on hand. 30 observations are there and the rating scale and the neural network architecture. I have taken the R program. Of course, we can do it in Excel solver also. I can show you. It takes time. So these input variables are brand, product, shopping, and then I have the outcome, which is a loyalty to be predicted, and I have the hidden layer with 5 nodes I have given, and the error that is minimized after 1528 iterations or so is 0.878, the sum of squares of errors. And the final weights are there here, for example. I think it goes out, but I don't know. Anyway, you can just see this. Final weights, inputs. Now you can see some of the weights are negative, some of the weights are positive. And I can just say in the R program or software, the classification matrix can be done. That it classifies. You can just give the threshold default probability, 0.5 or so, it classifies. But from this, if you have to write the equation, loyalty is equal to, it will be very difficult to write the architecture. So what I have done is take the neural network architecture and the output as it is. Don't change anything, because if you run it again, it will give another set of weights. And using the weights, the software predicts relative importance. But weights themselves are problematic, some negatives, some positives, and different hidden layers weights are also you will have to take into account. So what I have done is, instead of the weights, I take the model and then try to increase, for example, brand by 1 more unit. The scale of 1 to 7, the existing input of brand, increase it by 1, brand becomes brand plus 1 in the rating scale, keep the product and shopping attitude at the same level, and see what is the change in the classification matrix, how the classification matrix changes. For example, the original classification is something like this, the neural network has predicted. How it changes, I have captured. Therefore, using the reference classification, which is the first one, without the sensitivity, and then running the model with increase in the brand, see the change, I have found out the odds, change in the odds in terms of enhancing the loyalty or decreasing the loyalty. And these odds are written here: brand, product, shopping. The least one is shopping. And in the logistic regression, also have put as a comparison the relative importance, brand, product, and shopping. Therefore, neural network has given product a little more, the shopping is a little less compared to this, and the relative importance percentages are normalized based on the odds. And 52, 25, 22 neural network says in terms of percentages, here it is about 54, 18 and 27.4. Now the graphics are there, neural and logistic regression. So it is somewhat comparable with a greater predictive accuracy, but it has also been able to capture the so-called black box conundrum, somewhat partially offset. I cannot say it's a white box because I can't write the equation, but this is the position, case study 1. And if you look at the classification, neural network is 90% accurate. Logistic regression is 84. And remember, it's a small data set. There is a general saying neural network doesn't work well for small data set. But even that is not the case here in this example. 84% logistic regression, the classification, 24 out of the 30 it has correctly classified. Neural network has classified 27 out of 30. So the question is, which relative importance should I take? Should I believe the neural network relative importance or the logistic relative, the regression relative importance? The answer is, go by the predictive accuracy. The predictive accuracy and type 1 and type 2 error, if you see, neural networks classification is much more authentic because it has predicted more accurately than the logistic regression. It doesn't mean that every case is going to be like that. This is one case example. And then I take another example from a classic work of Paul Green, Analyzing Multivariate Data, a books by mail, where mailing strategy is worked out on 1,000 records on recency of purchase and the number of arts book purchased. It's called the Art History of Florence to 1,000 existing customers. Only 8.3% bought the book. Art History of Florence, whether the purchase of the book, can I predict, is a function of number of months since bought and number of arts book bought. That is the example. And in this example, when I did this, this is the neural network architecture. The input variables are months and number bought, and then the output is purchase 0, 1, and these are the synoptic weights, and these are the weights connecting to the hidden layer to the final. So that is the second part. And then in this case, similar to if months are increased by one more month. In other words, generally in the purchase of books, you know very well, if I have bought it in, let's say, in April, and 5 months have passed, I have not bought, let's say, then as the number of months delay gets more and more, it is very unlikely you will buy. Isn't it? And then the number of arts books, if you start buying more, then the art history of Florence, you may be able to buy. That is the model. So logistic regression and neural network, the number bought has a relative importance of 84%, whereas the logistic regression, it is 74%. And months, it is 25.74. In neural network, it is 15.95. So we are able to quantify the whole thing. Okay. Now, the relative importance, if you see here, number bought, 74.26, 24.94 for logistic regression, neural network, 15.95 and 84.05. So which is more accurate, if you see? The classification matrix, neural network overall accuracy is 92.4%. Logistic regression overall accuracy is 92.2. It's very marginal. But if you look at this, out of the 83 people who actually bought the book, neural network has predicted correctly 14 people have bought the book. Whereas logistic regression, it predicts correctly only 8 out of the 83. Now, of course, I have used the default cutoff point of 50%. One may argue in a mailing thing, even if the probability is 15%, you are very likely to buy the book. I have not changed the cutoff. I have taken only 50%. So if you take the type 2 error and the overall accuracy, neural network has done a remarkable job in terms of the accuracy. And this is the relative importance. So what I'm saying is some broad conclusions I'm drawing. Both the case problems, they reveal that neural network gives better accuracy, excellent predictive accuracy. It even gives better accuracy than the logistic regression in terms of the classification. The relative importance of the attributes or the input variables can be quantified as much as a logistic regression with a little more efforts. Then the sensitivity analysis can be done in the neural network. If you don't change the weights, if you increase one parameter by some unit and keep the rest of them constant, how it changes the classification matrix, and from that you find out what is odds. I just want to say odds divided by odds plus 1 is equal to probability. Odds is equal to probability by 1 minus probability. So you can easily work it out and simulate the experiment of the neural network architecture. Don't change the weights, just run the program with different sensitivity scenarios and then try to gauge, is it possible? The answer is yes, you can do that. So I'm saying neural network is not a complete black box. It's also not a white box. However, adequate whiteness can be derived from the black box. This is one thing which I say with all confidence level. Then the sixth point is, if you are interested in testing of hypothesis, there is generally a traditional statistician. I am also a statistician, but I am just saying I have an open mind. The traditional statistician, statistically rigorous thing. See, logistic regression, I have a McFadden R squared. I can talk about the uncertainty of the intercept model that has been captured by the full model. I can interpret the odds. I have a precise estimation of the parameters using the log likelihood estimation. I can test the hypothesis of individual coefficients 0 or not. I can do all that. Here you have some weights, you are getting some weights, everybody is getting some weights, and we have to wait. There is no hypothesis possible. So hypothesis testing is not possible in neural network as a matter of principle. You may try, you may dig in, you may try to do some research. It's not easy, it's not possible. And therefore, logistic regression in that sense, it's robust. You have same thing, I run logistic regression, I will get the same estimates. It will not differ. That's a problem. Why it happens in neural network is because that neural network gets stuck with local optimum. When you have got a curve, it changes the direction. Several minimum are possible. It may get stuck with one local optimum, and the global optimum becomes a challenge. So you'll have to run the weights, you'll have to change, you'll have to do all that. So hypothesis testing is paramount, then neural network is not an appropriate model to use. That we have to accept. That's the strength. Now the question is, as a manager, as an analytics professional, as a person to take decision in a very complex world where you talk about machine learning, automation and all that, you will have to strike a balance between predictive accuracy versus hypothesis testing. So, predictive accuracy with fair amount of explanatory power may be preferred to hypothesis testing capability with less accuracy. Which one would you choose? That's the question. I can't say you should choose this. I'm saying predictive accuracy with reasonable explanatory power is preferred to hypothesis testing capability with less accuracy. Which one to choose? And therefore I say, in the world of analytics, neural network is a very strong contender for classification and prediction as part of the supervised learning. So it is not a complete black box. It is not a complete white box, but substantial whiteness can be derived out of the black box. And therefore, I am trying to say, with more case examples I can pick up, that neural network is indeed not really speaking a complete black box. Is neural network a complete black box? Is it a black box? The answer is no. I'm not saying it's a white box, and that is the conclusion. So it's not a complete black box. So I stop here for questions. We will interact, and then we'll just go for lunch. Yes, sir.
Thank you so much for this nice presentation. Sir, I have a problem regarding, as you mentioned that for neural network, the primary challenge is that we don't have y-equal to fx kind of reaction, and different results may give you different output. That means reproducibility is a problem. So I primarily deal with risk model for UK, and there are some regulatory bindings. So we have already provided through some POC kind of thing that neural network is giving me excellent lift in terms of good bad prediction or something like that. But the problem is that we are unable to convince them when it is coming to the deployment, because to some extent, as there is no equation readily available, so in spite of having great result, they are little concerned about whether there will be any inherent error and which will result adversely in the long run.
Yeah.
So my question is, sir, what is your suggestion in terms of this type of risk model situations?
Yeah, that's true. The acceptability factor is a problem, because SEBI, all risk management people, they swear by logistic regression. That is a fact. And I also want to take this opportunity to tell you one more technique which is less popular in the analytics world, but much more robust sometimes compared to the logistic regression, is the multiple discriminant analysis model of Fisher, Ronald Fisher. And if Fisher had discovered perhaps multiple discriminant in the year 1928 instead of 1936, logistic regression perhaps would not have taken off. You may think it is a provocative statement, but you will discover it's an outstanding technique. So this explanatory power taboo, therefore they don't believe. But what you can do perhaps over a period of time is, along with predictive